So today our speaker is Dr. Fabiano Rodrigues from University of Texas at Dallas. So Dr. Fabiano Rodrigues is an associate professor of physics and electrical engineering at the University of Texas at Dallas. He received his master's degree in space physics from the Brazilian National Institute for Space Research in 2003 and his PhD in electrical and computer engineering from Cornell University in 2008. His research interests and experience including studies of the low-latitude ionospheric electrodynamics and irregularities using various types of measurements. So today he will talk about ionospheric irregularity and scintillations. So we know that this topic is not only of very high scientific interest, but also very high societal interest because of this scintillation irregularity impact on GPS navigation and communications. So, so Dr. Rodrigues, please go ahead and start.
Hey, thank you. Thanks for inviting me to be here. I wasn't really quite sure. I know people at HAO know a lot about the ionosphere and irregularities, maybe more than I do, probably more likely, very likely more than I do. But I didn't know what the audience would look like for this presentation. So I put together a few slides and a few things. And in the end of the day, it's going to be a shameless promotion of some of the work that I've been doing with some grad students in terms of instruments, new instruments for observation of equatorial spread F, ionospheric irregularities, and scintillation. So the way I thought I would put this presentation together would be, I'm going to start with some introduction. I'm going to talk about equatorial spread F, my simplistic view, perhaps, of what I think it looks like. And then I'm going to talk about ground-based experimental studies of spread F. I'm going to tell you a few ways that we can measure spread F. Some of you might be familiar with it, some might not be familiar. And when I do that, I'll move into new observations of spread F with this AMISR 14, which is a new instrument that I've been working on. And I'm going to try to emphasize what we have right now and what I think we might need in the future in terms of observations, two-dimensional observations, and the implications for some of the things we wanted to learn about spread F. And then I'm going to talk about SynPy, which is a new low-cost sensor that is capable of measuring L-band scintillation and also derive ionospheric total electron content. And I'm going to try to do an introduction of these things prior to going to the instrumentation part. And hopefully you might find at least this a little bit entertaining. So I'm going to start by showing one observation of ionospheric irregularities that have been made by a satellite that was launched many years ago, the CNOFs. What you see here in this slide here on the top panel are measurements of the ion density performed along the trajectory of the satellite. And you see these perturbations in the density, and you can see the average that is in black matches the sampling rate, the high sampling rate of the measurements in most points. But there are some points in here in that green in the night side where you have large fluctuations in the ion density. And we refer to those observations as a spread F. And the spread F, for most people, is defined as the signatures of low latitude region irregularities over a wide range of scale sizes. And it goes down to centimeters. If you have, depending on the instrument you have, you're going to be sensing centimeter scale irregularities, and some other instruments are going to be looking at tens of kilometers or maybe hundreds of kilometers irregularities. And Patrick Roddy, who put this slide, this plot together, he has a spectral analysis of the ion density measurements made by CNOFs during that path. And it's interesting, and not too many people realize about those measurements made back in the day, is that they had a sensor that would measure ion density at 512 hertz, which would allow us to make measurements of scale size irregularities down to a few tens of meters. So you can measure, kilometer scale size irregularities, but you can also see in this spectral analysis irregularities that are a few tens of meters. And that's an interesting, it just shows you the wide range of scale sizes that you can observe when you have a spread F event. Then the next step that we need to revisit is how those irregularities are created, and it basically goes back to Rayleigh-Taylor instability. We refer in the ionospheric community, we call to the generalized collisional Rayleigh-Taylor instability. And the scenario that we have is this, especially around sunset hours, we have this steep gradient in the bottom side F region of the ionosphere directed upward. And we have currents flowing in the ionosphere as well, driven by gravity or by a background electric field, E0. And if you have that scenario, and it so happens that you have a perturbation in the bottom side F region, to keep divergence free, the current divergence free, you're going to have a polarization electric field created in that perturbation delta N that is indicated in that slide right there. And that will produce an E cross B drift, which drives the plasma, the low density plasma upward. And this is basically the basic scenario that we have. You can linearize the plasma equations and get a growth rate for that initial perturbation. And the growth rate is going to be something, if you just take into consideration local plasma parameters, it's going to look like something like what you have at the bottom of the slide here, that equation. They're going to depend on the scale length, how steep the gradient is in the bottom side F region, and it's going to depend on the ion neutral collision frequencies, nu IN right there. And it's going to depend very heavily, as I'm going to show you, on that E naught divided by B naught, which is the upward E cross B drift. So a lot of people have studied in the past, they try to relate the drifts to the spread F, and we have a good understanding that that's an important parameter to drive ionospheric irregularities and the disturbances that lead to ionospheric irregularities, at least at low latitudes. And this, I promise you, it's the only model plot that I'm going to show you, well, that I made, at least. The next one is going to be a model, but it's a very interesting one. But this is a pedagogical kind of plot where you take the background electric field or the background drifts, and you input in a model like SEMI2, which is a physics-based model, and you drive, and you calculate using the outputs of the SEMI2, the linear growth rate. And you're going to see that the linear growth rate increases. It's that color-coded on the top plot right there, increases around sunset hours, right at the time when you see this increase in the E cross B drift. And this is fairly well known. It explains a lot of things that we see. We see a lot of irregularities around starting at the sunset and then going up to midnight and maybe longer. And just it tells you the E cross B, that term that you have in the linear growth rate, tells you that during that time the conditions are favorable for the development of these irregularities. And there's a cascade of irregularities of the process is taking over and with producing different scale size irregularities. And to prove that the E cross B, I'm not gonna, to prove that the E cross B is really a factor, a dominant factor, important factor in controlling whether or not we're gonna observe irregularities, I'm using this plot from HAO sub Q from a few years ago, where he basically said, hey, this is the spread F occurrence rates that I observed with RockSat, and that's the plot on the top, color plot on the top here. And at the bottom, it's the magnitude of that PRE, of that pre-reverse enhancement drift that I tried to simulate in the previous slide. That's the magnitude. And you can see the two patterns, they look very alike. And it tells you that the E cross B drift is really important, dictating where spread F is going to occur. And this is fairly well known in terms of climatology. What we think we're moving towards is trying to understand what, in a day-to-day variability, how responsible the E cross B drift is going to be alone for the development of irregularities. And I'm going to try to illustrate what I mean by that in the next few slides. So if you look at the daily case and I look at the E cross B drift, can I tell you whether or not spread F is going to occur just looking at the E cross B drift? And the answer is probably not. But we wanted to know to what extent that E cross B drift is responsible. And more importantly, as an experimentalist, I'm going to try to convince you that we might not be doing the perfect job in defining what spread F is and observing spread F. So that's why I've devoted some time trying to figure it out how to do these two-dimensional observations of spread F at low latitudes. The other thing that I think we were looking forward is to understand times where we see what I call atypical spread F, are spread F events that occur, that we observe and occur at times where we didn't expect to see them. Like in June solstice, if you look at the American sector around minus 70 degrees in longitude and June, July, you don't expect to see a lot of events in there. Very, it would be, if you're looking from a satellite point of view, you're not going to see anything. But it turns out that in the past, solar minimum, we saw a lot of events during that period, and we didn't expect to see them, and we're still trying to understand what is the main source and what are the sources, the potential sources of those events. We have some hypotheses. In terms of modeling, the growth rate, the linear growth rate, it's an interesting starting point. It tells you where, based on the inputs that you have, where you are likely to see spread F. But people that are much better than I am with computers, they develop models that are very realistic, and they not only predict what the linear growth rate is, but they tell you what the nonlinear evolution of spread F looks like. And if I can, I'm going to try to play a movie here from Yokoyama's model, and it shows you what spread F looks like from a model point of view. And based on my own view of this modeling outputs and looking at what I've observed with radars and some studies from other people, it looks very similar to what we've seen, the morphology or the evolution in height. But we still have very limited observations, two-dimensional observations of those structures. And I feel that I should be devoting a little bit of time trying to get those two-dimensional observations in place for the community and for myself to better understand whether the models are doing the right thing, and also whether or not we can relate the spread F observations, the events that we see, to local conditions of the F region. So this is, if I had in mind what I wanted to have, this would be something that I would like to have, a snapshot of the densities as a function of longitude and zonal distance and altitude, which tells you what the structures are in this magnetic equatorial plane. And this was made by a radar system that is capable of making measurements of the electron density. And it's a steerable antenna that is attached to this radar system, and it goes back and forth and can make these measurements and takes pictures of what the ionosphere looks like at the time. But a system like this, like Altair in the Pacific, is not currently available for us to use all the time. And we wanted, from my point of view, I wanted to maybe have a system that we can do this in a more regular basis at a site that is more available to us. And that's what I'm going to try to talk about about these things. And the other thing is that I wanted to say, I want to emphasize is, if you have a site that is measuring the conditions of the F region at a single point, like let's say drifts, or let's say the height of the layer, and to what extent those conditions are related to the spread F that you observe. I'm going to try to show you some examples where I can have a large PRE and not have spread F, and one can say, hey, it might be some other factor that is playing a role, like winds or conductivities, which play a role in spread F, but it also might be that I'm not making the correct observation of the spread F, and I'm missing the spread F that occurred just a few tens or hundreds of kilometers off the site. The other thing that I wanted to talk to you about is this low-cost scintillation and TEC sensors that my grad student has been working on, and I've been working on for a few years now. and we have developed some capabilities. Now, what I wanted to emphasize is there are commercial receivers capable of doing that. They are a little expensive, and usually you are not going to put them very close together, and you can have a clear picture of this evolution of spread F and the impact under different stages of the evolution of spread F. So if you have a low-cost sensor that you can put in a dense array, then you can image or you can observe the evolution of spread F at the various stages, and you can estimate what the spread F impact is on the signals, but also you can probably derive some important information that is going to help us to better understand the genesis of spread F, and at least the morphology of the events. That being said, that's the introduction, the spread F part, what I think spread F looks like and where it comes from, our current understanding. And we wanted to understand a little bit more about the day-to-day variability and the impact on signals. Now, the next thing that we need to have is a site where we wanted to make the proper observations, and and the site that I'm biased towards is the Jicamarca Radio Observatory in Peru, which is located at the equatorial, the magnetic equator, at the place where we think the irregularities develop. And it's a site that has been operating for several years and has several features that are advantages to that type of study. So once you realize you wanted to make experiments, now the first thing as an experimentalist you want to have is a site like Jicamarca. And Jicamarca provides with a place where the magnetic field doesn't change much with time. If you go to Brazil, for instance, and you install an instrument at the magnetic equator, in 10 years, that instrument is not going to be at the magnetic equator anymore. So the secular magnetic variations in Peru are very small, and we have been under the equator for several tens of years now. And the other thing is you have technical staff that is very knowledgeable, and also you have co-located instrumentations that you can do comparisons with other types of instruments, and you have the right place depending on the footprint of the instrument you have to place the instruments in there. So there's various factors that I think Jicamarca check the boxes, and I've worked with them for several years, and I'm kind of biased towards them. It's also the only site that we have that in the American sector that would be allowing us to make this type of observations. I had a site in San Luis, a radar, that I had to move to Jicamarca now for several technical reasons. So at Jicamarca, we do several measurements that I have interest, and we do two types of measurements at Jicamarca right now. We do that I am involved. One is the radar observations of the ionosphere, and the other one is the satellite beacon observations. So the first one, in terms of ionospheric radar observations, we have two types of radars. And both radars, they take advantage of scattering of electromagnetic radio waves from plasma waves that match the Bragg condition. For a monostatic radar system, that means that the radars at Jicamarca that operate at 50 megahertz, they will be sensitive. They will respond to plasma waves that have wavelengths of 3 meters. So that's when we send pulses and we get scatter back, they're going to be from waves that have that scale, size, or wavelength. The scatter that you get back is two types. The first one is the incoherence scatter, and we call it incoherence scatter radar technique. And the scatter comes from ion acoustic waves. Those waves are tiny amplitude types of waves, naturally occurring waves. They are there all the time, but they have an extremely small radar cross section. What it means is the scatter back is really tiny and requires megawatt transmitters and a large antenna system to be able to collect the data, to collect the signals and differentiate the signal from the noise. And that's why we have a 300 by 300 antenna system at Jicamarca to make the measurements. The upside of that type of instrumentation is that there is a very well developed theory for the radar cross section. So once you have the measurements, you can do nonlinear least squares fitting to the data, and you can derive parameters from the measurements like the plasma ion temperature, electron temperature, velocity, density, and ion composition. These are all important parameters that you wanted to have prior to spread F evolution, so you can have a state of the ionosphere prior to spread F or prior to absence of spread F, so we can understand what is the state of the ionosphere leading to spread F or inhibition of spread F. Then we have coherent scatter radars, which instead of scattering from these ionoacoustic waves, they scatter from field-aligned irregularities such as those associated with spread F region irregularities. These waves, they have large amplitudes, so the radar cross-section is a lot larger than the cross-section that we have for incoherent scatter. And as a result, to make observations of those waves or irregularities, we don't require a large radar system. You can only use a fraction of the antenna that we have at Ricamarca. We can use just kilowatt power transmitters, and we can make measurements nearly continuously 200, 250 days a year without being concerned about energy power consumption. The downside is that we don't have theory relating the observations to plasma parameters, but still those observations with in coherent scattered mode allow us to tell where the irregularities are in height and in time. So in the end of the day, a lot of you are familiar with this type of observation. If you go to Ricamarca and if you use the database, you're going to have measurements like the one I'm showing in here. This is an example of an incoherent scatter radar observation made on April 2 of 2004. And on the top, what you have is the signal to noise ratio that you have for the observed echoes as a function of local time and height. You see the echoes are really weak during most of the day. They are incoherent scatter echoes. They are from ionoacoustic waves. But then when you get around 19 local time, you start having echoes that are stronger, and those are coherent scatter echoes that don't come from the ionoacoustic waves anymore. They come from the irregularities. So what I'm trying to tell you now is that you have most of the day these observations of the plasma, the quiescent plasma, and then you have these observations of the turbulent plasma made by the same system at the same location. And you can see at the bottom here, what they use in this day, the measurements are to derive the upward vertical drifts, the drifts that I mentioned that are really important for spread F. So you can see around 18 an enhancement of the drifts, and then the spread F over right after. So you're inclined to think, hey, we had a large PRE on that day. As a result, we got this spread F event, just like what we had in the simulations that I showed in the beginning. What I wanted to point out here is that when you do an observation like this, you have a single point direction, nearly vertical, and the beam is really narrow. It's just a few degrees above your head of zenith angle, or zenith angle. So what you have is this being on the left-hand side, and you don't have information in the east-west direction, unless you are clever. And what you do is you, instead of making measurement with the whole system, you just distribute modules of antennas in the east-west direction, and you create baselines, and you do radar interferometry. Now you have the RTI map on the top right here, and you also have this, what is called in-beam images of the distribution of the irregularities within the beam. This is called radar imaging, or coherent scatter radar imaging, and what you get is the distribution of irregularities within a few degrees of vertical. Not much, but you have some information in the east-west direction. So what I'm working on is to get information over a wide field of view, angles that go up to 30 degrees off vertical and would go up to several hundreds of kilometers in the east-west direction. Rather, this one is just a few tens of kilometers. So this, the main point for this past few slides is that the radar systems can give you information about the plasma, but those measurements are made just a few days a year, maybe 20, 25 days. And then you have information about spread F by coherent scatter radar modes at Ricamarca, and those are for 200, 250 days a year because they use less power. You can do measurements of the ionosphere on the same location using beacon satellite signals. If you're transmitting two coherent signals of different frequencies, F1 and F2, you've heard of this very much, I imagine, that you can derive the total electron content from those observations. And it's a simple technique, remote sensing technique. You just look at the phases of these two signals, and the difference in phase is going to be related to the total electron content, or the integral of the electron density in the path between the satellite and the receiver. And that's a very important measurement that you have, because now you have not only GPS, but you have all these constellations flying over your head, and you can image the ionosphere and measure the ionosphere at a given point over different locations in different zenith, azimuth angles and elevations. You can also use diffraction. Now things start to become a little bit more complicated. This is the case of a quiescent ionosphere. This is a case of a turbulent ionosphere when you have irregularities. What I try to illustrate here is that the plasma is dielectric, so it has this index of refraction associated with it, which is related to the electron density. You can replace that ionosphere, that disturbed ionosphere, with a phase changing screen. That's the effective effect of that ionosphere, is changing the phase of a wave, plane wave, that is propagating through the ionosphere. And that wave is going to propagate all the way to the ground. And if you had different receivers in the east-west direction or north-south, you're going to see patterns. And those are going to be a result of constructive and destructive interference of the phase fronts that arrive at that given point. And that I-X in here is a illustration of what the intensity of the signal would look like on the ground. And because the irregularities that are causing that change in phase are moving, you're going to see, if you have one receiver located at one given time, that spatial variation is going to convert into a temporal variation observed by a static receiver. The other thing that is important is there's this equation here that is phi I of k, which is the spectrum of the intensity, the spatial spectrum of the intensities on the ground are going to be related to the spectrum of the phase variations, the spatial spectrum of the phase variations, controlled by the sine square factor here, which is the Fresnel factor. What that Fresnel factor is telling you is, even though you have that spectrum of irregularities, the irregularities that are going to be controlling the fluctuations are those that are of the order of this RF factor here, which is the Fresnel radius, and it depends on the wavelength of the signal and the distance of that phase changing screen. If you are like me using signals in the L band, the irregularities that are causing these fluctuations in the signal in the phase and amplitude are irregularities that have wavelength around irregularities that have a scale size of about 400 meters. The other thing that I wanted to emphasize before we move forward is, now you're measuring these intensities, these fluctuations by a static receiver in the intensity of the received signal. Most of us that study ionospheric irregularities using beacon signals, we compute this S4 index, which can be defined simply as the normalized standard deviation of the signal intensity divided by its average value. And that S4 index is proportional to the absolute density variations. So in places where you expect to see large density variations, absolute density variations, you're going to see stronger fadings in the signal, and as a result, larger values of the S4, which go from 0 to about 1 most of the time. This is what scintillation looks like if you haven't seen it before. So this is a typical case that if you go to low latitudes where the density is not at the equator, but off the equator at the equatorial anomaly, you see large fluctuations. You can see on the top the TC measured by a dual frequency GPS receiver, and at the bottom the signal intensity. And you can see the TC is really smooth until about 20 local time, and then it sees spread F or ionospheric irregularities, just fluctuations in TEC, and the signal starts to fluctuate and to scintillate as a result of the diffraction caused by those irregularities. So here, is where I wanted to start talking about what do we need, or my personal view in terms of observations and what I have spent time looking at, trying to come up with new observations of spread-F. I tried to do my best to give you an overview on the scenario where of observations and what spread-F is. And now I'm going to tell you a few of the things that we've done in the past and that motivated me to have this two-dimensional picture of spread-F. Like I said, at Hickamarka right now, we can only make, up to very recently, we can only make these observations mostly in the vertical direction. What we want is that we be able to observe spread-F within a few hundreds of kilometers in the east-west direction, and that will be important. It's going to be important, and there's many reasons for that to be important, but I thought I would just make it explicit in terms of some questions that we wanted to address. The first being, to what extent does the PRE alone control spread-F development? And I'm going to try to explain these things later on. The second one is, are observed post-midnight spread-F events generated locally? And the third one would be, do equatorial drifts play a role in the post-midnight SF development or in the post-midnight events that we observe during solar minimum and sometimes during moderate solar flux conditions as well? So I'll try to be a little bit more clear here with respect now with the first question. To what extent does the PRE alone control spread-F development? So in the past slides, I showed you a case where we had this very strong PRE and then spread-F developed later on. This case here, you have another measurement where you have on the top the vertical drifts measured by Hickamarka. The middle panel, my student said, hey, I'm going to look at the SNR values. I'm going to identify coherent scatter echoes. And I'm going to say, I'm going to come up with an index that tells whether or not spread-F, how strong spread-F is. And the index is basically the percentage of the area between 19 local time and 24 where echoes are observed. So if very few echoes in that window are observed, then spread-F is really weak. But if most of that area is covered, then the number is going to be 1 and spread-F is going to be strong. And then we derive the magnitude of the PRE. But I don't need to go into the statistical study to tell you, you can see in this event here, the PRE, the magnitude of the PRE is somewhat large as 25 meters per second, and the spread-F that we see vertically does not get to high altitude. It's just limited to the bottom side F region. And the spread-F in the bottom side F region appears almost every day. It might even be related to some other type of instability. But you see, it's a case of having a large PRE and not spread-F, and what that might be just a limitation of the observational capability we have. And I'm going to try to explore that later on. She did a little bit more study where she said, hey, the vertical axis here is how strong spread-F was, and in the horizontal axis you have the PRE peak, and you can see several cases where the PRE was really large or significant and you don't see much spread-F. The other question, and to answer that question, we would need two-dimensional observations. It might be the fact that spread-F just developed as the plasma is moving to the east. We just missed the occurrence of spread-F. Spread-F developed vertically to the east of the site. We just missed. So that's the point that I have. The second question is based on several things, but there is a study that another grad student of mine did. He said, hey, Dr. Rodrigues, we have just coherent scatter observations made for over several years, from many years at Hickamarka. Let me put the occurrence rates as a function of equinox, solar local time, and height. And let me take a look how spread-F behaves as a function of a solar flux. And this is a busy plot, what you're seeing here, but it's telling you right there for each year, each row, it tells you the occurrence rate of irregularities as a function of local time and height. The left-hand side panel just tells you the solar flux the average solar flux for that season. But what the main point of this plot is that spread F is during moderate to strong or moderate to high solar flux conditions is contained in the pre-midnight sector. But when you go to solar flux conditions, those events appear in the post-midnight sector again. Then the next natural question that one would ask is, well, are those events that we're observing in the post-midnight sector, are they being generated locally? Are we just observing the result of a spread F that is appearing at Hikamarka, or are we just observing events that have occurred at other longitude sectors and drift into the field of view of the radar system? So if you have a system that measures two-dimensionally, then you can track the origin of these irregularities. Are they drifting from outside the field of view, or they are generated within the local area of the Hikamarka? You can unambiguously determine whether they are generated there or not. So that's another question that we have in mind. The other hypothesis that people have put forward is that is related to the origin of these post-midnight events. So the pre-midnight events are associated to the PRE, and you see the electric fields are important in that growth rate. Can it be that the post-midnight events are also associated to abnormal drifts in the post-midnight sector or in the midnight sector? In other words, can the events that we observe in the post-midnight sector be caused by abnormal weakening drifts or upward drifts that we've been seeing in the midnight sector? And my grad student went to the database and looked at occurrences of spread F in the June solstice, where we didn't expect to see spread F, and he saw this prototypical event here that you see. I don't have the time. This is from June 4 to 5 on 2008, and you see an event occurring in the post-midnight sector. But it's because it's running the Hikamarka ISR. You also have the drifts on that day. And the drifts are those black markers that you have in the bottom side there. Those are the mean F region drifts. And you can see the drifts start to weaken as they go to midnight, and then spread F occurs. But then we are left with the question, is this event really generated by the vertical drifts? Or just so happens that during those conditions, a plume drifted across the field of view of the radar, and we happen to see an event at that time. And because we don't have a lot of events to detail to see this, it becomes really difficult to make a strong point about the association between the electric fields, these drifts, and the spread F. Another thing is, if you calculate the growth rate for that event, for that drift, you're going to see that the growth rate are not really large compared to what we see in the pre-midnight sector. So all those little things that I'm telling you is just trying to tell you, hey, I think a two-dimensional picture of spread F, the evolution, the genesis, decay, development would be important to have for us to better understand the evolution of spread F and how they relate to local conditions. So now what I'm going to show you is what we have right now and what we've been working on. So many of you might study high latitude ionosphere, and you know there's this A-Miser system. I highlight two versions, one in Poker Flat and one in Resolute Bay, and they are capable of doing coherence scatter, and they have a capability of electronically steer the beam. So you're literally a really nice system to make observations of the ionosphere. You can point the beam in the direction you want, and you can have parameters derived from those directions, and you can have three-dimensional pictures of the ionosphere and parameters. And it's really just a great instrument to have, but we don't have one at Hikamarka. What we do have, instead of this system that has 128 panels of antennas and delivers 2 megawatts, is this system. which is, instead of 128 panels, it has a 14 panel, and instead of delivering 2 megawatts of power, it delivers 200 kilowatts of power. And it's part of an MRI to UMass, and ended up at Hicamarca in 2014 for tests. It had technical issues, it stopped working, it made just a few measurements, we tested it, and then I got involved later on, and in 2019 we got some funds to repair the system, and now in 2021, despite all these problems with COVID and Hicamarca being closed, these guys did a magnificent job, and they make the system to work again. So what I'm going to show you is just one example that illustrates a lot of things with that system. So in July, we did this experiment, and the experiment in simple words is this. Hey, let's just do coherence scatter. This cannot do incoherence scatter. We cannot derive parameters. We can just do measurements of irregularities, but we can steer the beam up to 30 degrees of zenith, of vertical, and we can image the magnetic equatorial plane as indicated in this polar plot on the right upper side in here, and the beams indicated here on the bottom. And we can do that with a resolution of 8 degrees in angle, and we can do that with a resolution of 3 kilometers in range. And we can have an image every 20 seconds. Those are the big parameters that we wanted to have for this. And what it's going to look like is this. This, what I'm showing here, on the top is the typical RTI map that we would have from a traditional radar system with a beam looking up. This is an event that you would see looking at a single beam. Very weak spread F prior to 22 local time, maybe around 22, 20, and 30, you see something a little stronger. And the red stripes, one thing that is interesting that you should pay attention is the red stripes on that RTI maps. Those are echoes from the Starlink satellites, I believe, that we see all the time now. And what you're going to see at the bottom here are two-dimensional pictures of what spread F, of what we got from this system. So as you see, the time passes by. What you're going to see is the first event. I don't know if you can see my cursor. You can see echoes coming from over Hicamarca, very weak, but then they just get stronger. And as they get stronger, they grow up in phase, in height, and they move to the east. At the same time, another structure comes from the west, and it starts to decay in the field of view of the beam pointed vertically. So really what you're seeing here on the top is first the start of a fresh event that then you missed when it was fully evolved to the east of the radar site. And the second event here around 2230 is the event that was generated to the west of the radar site and is decaying in front of Hicamarca. On top of that, around 1 o'clock now, you're seeing post-midnight events to the east of the radar site. If I go back here around 1 o'clock, what you're going to see is, right here, I don't know if you can see my cursor, but at the bottom you see spread F to the east of the radar site that you would have missed looking up with a traditional beam. So these are the things that a system like this would provide to Hicamarca. Now you can better correlate the local conditions to what spread F looks like later on. There are a few points that I wanted to make. This is just one of the examples of the measurements that we made with the system. We start making it with the system. The first point is that if you're looking in one single direction, you're missing a lot of activity, spread F, irregularity activity. If you have multiple beams like this one, then you can see the evolution of the fresh. You can distinguish fresh from old structures. You can actually capture events that were not overhead that you might have missed. And if you squint your eyes on number 4 here, what you're going to see is you see events like pre-sunrise spread F that occur to the east of the site, but you would have missed if you're looking vertically. So those are an infrastructure, an observational instrument that I think is going to provide new information about irregularities in spread F that will be able to use in the future to advance understanding, basic understanding of spread F. So this is the first result that we got in terms of instrumentation, and that's our efforts related to radar observations. Next is we switch gears now from the radar systems to the beacon signals. And what I wanted to do now is to tell you that my students and I, we've been working on this low-cost scintillation and TC monitors using off-the-shelf GNSS receivers and controller boards. And that type of system allows for several things. It allows for educational initiatives, and you need to keep in mind that as a professor, I have to be engaged into educational activities as well. But it also provides for citizen science initiatives that I'll talk more about later on, and research that requires daisy observations. What I'm going to tell you about the instruments that we're working on are not going to replace the commercial receivers, but they can provide measurements that would allow us to address some science questions that would be prohibitive if you needed to have a dense array of the commercial receivers. The other thing that motivated me to spend time on this is this type of study that we just published a few months ago. In 2002, Litvina and et al. Reported the first intense mid-latitude L-band scintillation, and was observed in Ithaca, New York, at Cornell, when they were preparing to deploy their scintillation monitor to low latitudes by mistake. Then when I came to UT Dallas in 2012, we deployed a commercial receiver at UT Dallas, and we made new observations, and we saw very intense scintillation, amplitude and phase scintillations over Texas, over Dallas, in a place, Dallas, keep in mind that Dallas is not like Ithaca, located closer to the low latitude region, is in a place that is far from the high latitude region, but is also far from the low latitude region, where we observed. There's a paper that describes the conditions also of the ionosphere during that event. And the reason, if you go back to the literature and you look for properties of scintillation, how does scintillation behave over the United States and how often they occur, you would find there is a lack of literature of observations, coordinated observations over the US in using adequate scintillation monitors, meaning scintillation monitors that are capable of making high rate observations of amplitude and phase. When I say high rate, larger than 10 hertz. We can use geodetic receivers that provide 1 hertz or 10 seconds measurements of TC and signal to noise ratio, but not high rate, which tells us the properties of the scintillation itself, like for instance, decorrelation times. So the example of questions you can address if you have a small system like that is distribute over the US and find out what are the properties of mid-latitude scintillation and how they compare with those of events at low latitude, which are known to be the strongest. And what are the conditions leading to the mid-latitude scintillations? You can use now with other instruments like Milson Hill. You can use with the TC maps over the US, and to try to figure it out, what are the atmospheric and geomagnetic conditions leading to those scintillations. For instance, are mid-latitude scintillations only occurring during geomagnetic disturbed periods? Can they be associated with other types of events? That's one simple question that you can address. You could do this with a receiver like the Septentrion one, which is the state-of-the-art of GPS or GNSS scintillation TC monitor. It provides every single information you need, triple frequency, phase and amplitude scintillation. TC has extensive documentation, has software for data analysis, for visualization, but it's somewhat expensive. It's $10,000 plus the antennas, $15,000, and then you need to be really concerned about the deployment and maintenance of these types of systems. If you have a system that is in the order of a few $100s, then it would be a game changer because you can deploy it more easily. You would not be too worried about maintenance. You could just simply swap receivers, not sending to repairs and come back. It can be used by students in student projects because you're not too worried about being damaged and things like that. So this is one of the things that motivated us to do this. And the first one that we came up with is this one that it costs about $100, and it can provide you with amplitude scintillation. It's basically a Raspberry Pi with a sensor, a Adafruit GPS receiver, and it provides signal to noise ratio with 1 dB resolution at 10 hertz. And you can go to Amazon and you can buy the parts and you can build it. I was a little bit more generous with the cost in there, but if you're cheap like me, you can get it under $100 looking for the right parts and discounts and things like that. And then to test it, we send it to a place where we see scintillation almost every day and a wide range of scintillation intensities, which was Presidente Prudente, which is in the equatorial anomaly peak. And we place it in parallel with a commercial receiver. And the results that we got for that very simple $100 receiver are exemplified by this. We calculated the S4. The S4 tells you the magnitude of scintillations. The S4 is shown here for the SynPy receiver, for the low-cost receiver, and for the commercial receiver. The commercial receiver is in red. The low-cost receiver is in blue. And the points that I wanted to make here is there's a very good agreement between the low-cost and the expensive receiver. The disagreement occurs at a low S4 values just because you have 1 dB resolution and you don't sample as fast as the commercial receiver. So if you're looking for weak scintillations, that is not the instrument right for your application or your intention. But if you're looking to scintillations that are larger than 0.2, which are the ones that really matter, you'll be able to detect with a system like that. The other thing that I wanted to point out is the downside of that receiver is that it has this threshold of 52 dB, meaning that even if the signal goes above 52 dB, it has outputs 52 dB. So if you have satellites at a high elevation, you're not going to be able to measure scintillation with those receivers. So $100, you can measure most of the time. For high elevation scintillation, high elevation signals, you might have trouble. But if you operate this for a year and you do a simple analysis, say, hey, I wanted to take a look at the occurrence rate of scintillation, then you're going to see things like this. You're going to be able to compare the septentrion receiver with the SynPy receiver, and the agreement is really it's somewhat good. But the SynPy tends to underrepresent the occurrence rate at the times just because we're missing those events at a high elevation. That being said, in terms of education, now you can go to this web page. If you wanted to build, if you're let's say that you're a modeler, you have been studying the ionosphere irregularities for many years, but you haven't done your instrument, you can go there. There's an instruction on how to build that system. The software is available. You can build it. And you can make your own measurements, and now you can say you're an experimentalist making observation of scintillation with that receiver. We didn't stop there. We have several, a few instruments. We have this SynPy 2.0, which is capable of making measurements of amplitude scintillation for multiple GNSS constellations. And we have SynPy 3.0, which is capable of making amplitude and phase scintillation measurements, but also make measurements of TEC for multiple constellations. And I'm going to show some examples. I'm running out of time here, but this is an example of measurements made with that SynPy 2 receiver, amplitude scintillations with a multi-constellation low-cost receiver in comparison with a commercial receiver. You can see over, up to 100 satellites a day. So your sky is going to be have measurements everywhere all the time, and you're going to be able to make scintillation measurements that are in very good agreement with a commercial receiver. This plot basically quantifies the agreement between the two. You can see the linear correlation, the coefficient of linear correlation between the two measurements is about 0.95. And if you feel that the commercial receiver is the true value, the standard deviation of the SynPy measurements with respect to that true value is going to be about 0.02 for the S4. And there is very little bias in the measurements, giving us confidence that one of these receivers are not going to be able to fully replace a commercial receiver, but you can address several science questions using a low-cost receiver like that. Now, the things that got a little bit more exciting are the TC measurements. So we created SynPy 3.0. We went to our lab. We put the two receivers together, the commercial one and the SynPy 3.1 together. The left-hand side, what I'm showing to you is in green, the TC from the code that is measured by the septentrial receiver. And the solid line is the phase, and the blue line is the elevation of the satellites. And I show you 4 examples of satellites in here. In the center column, you see the same measurements made by SynPy collocated with that receiver. And you see on the rightmost column here, a comparison between the phase TC from the two receivers together in the same plot, and they're virtually the same. You can see that the SynPy is even capable of capturing delta TC that are smaller than 0.1 tech units. So we're being very happy with it to the point that we felt ready to deploy it at Jicamarca. We deploy it, it's separated from a commercial receiver in there, so we use the cheaper antenna as well. And the results that we get are something that can be exemplified by this plot right now. On the top, you have the TC you can barely see, but in black, you have the TC from the septentrial receiver, the commercial receiver, and in red, you have a TC measured by the SynPy receiver. In the bottom, you have the S4 for the two frequencies, SynPy and septentrial. And you can tell the agreement is really good, even though these receivers use different antennas and they're spaced by a few tens of meters in the east-west direction. The other thing from the scientific point of view is that I wanted you to pay attention is, if you look around 7 universal time, which is 2 local time at a Jicamarca, you see strong scintillation events, and those are associated with post-midnight events. This is unexpected. At equatorial sites, the densities are very low, so the delta N is expected to be very low, and we don't expect to see strong L-band scintillations in that location. But we ended up seeing, not only in that location, somewhat strong scintillations, but those occurring in the post-midnight sector where you would think the densities would be even lower than during the pre-midnight sector. This is another example showing somewhat strong scintillations. You can see in altitude, the frequency is lower and the scintillation is stronger, and you see TC in there as well. And you can see some interesting facts in here. If you see between 2 and 4, you have density fluctuations in TC, but there is no scintillation in there. So the irregularities that are affecting spread F that are causing scintillation might not be present during that time. We also built a system that if you have one of our systems and you plug in an internet, it will automatically daily maintain the system, make the observations, and send to a server. You will collect the data, organize the data, create netCDF files with the data, put them organized files, and we're going to make available to collaborators. This is a system that my grad student is working, and we have a prototype already, and we just need to test with a few sites to make sure that we can start distributing this to collaborators so they can have access to their folders of data. So this is all, we have prototypes for all this already in some tests done. That being said, I'm going to stop in here. So these are the two systems that we have that I've been working on. One is the 2-dimensional radar observations of spread F, and the other one is SynPy, which will provide low-cost observations of scintillation and TEC. And I think I'm hoping that both instruments are going to be able to help us to advance our understanding of ionospheric irregularities and scintillation as well. I'll stop here. I'll take questions.
Okay, thank you, Fabiano, for a very nice and informational talk on current state-of-the-art observational capability on for irregularity and scintillation. It's very exciting, very promising. So we are running out of time, but let's use a little bit extra time for maybe a couple of questions. So questions? Okay, so I didn't hear very, when you talk about the AMA is 14, it's 2D range. So one dimension is the altitude, the other dimension is the longitude or
zonal distance, longitude.
Zonal, it's zonal. Okay, okay.
The reason you don't do east-west is because for coherent scatter, you need to be pointing perpendicular to get scatter from the field line irregularities. And when you point in the east-west, in the north-south direction, you don't get that perpendicularity. So that's why we keep in the magnetic equatorial plane.
Okay, okay, makes sense. Yeah, and it sounds like with the sign in Scintillation, if you do a distributed system across different places, maybe you can determine whether ESF is like developed locally or moved from other place.
That's correct. So the first thing, the most obvious thing is a lot of people in the past have done these correlations between, hey, this is H prime F, this is HMF2, and this is spread F, and the correlation between the two. The point that we can make here is there might be times where you don't see spread F is just because the events were not observed by the local instrument. It's just the event took some time as they drift zonally, you miss those events. So the lack of correlation in some of these studies might be due to that.
Yeah.
So I didn't talk about this, but people talk about large-scale wave structures as well. There's a way at Ricamarca combining air glow measurements to look at large-scale wave structures, and then you have this two-dimensional picture of spread F, and you can see the correlation between the spread F development and these wave structures. In other words, all the time when we see this two-dimensional wave structures in air glow, are they correlated to the development of spread F or not? So this is another topic that I think a lot of people might have interest on.
Yes, and I hope that modeling capability can be significantly enhanced, increased in the next few years to work with this modeling capability. Yeah. Okay. Thank you. Thank you again, Fabiano. And so this concluded today's colloquium. And everybody, bye. So enjoy the rest of the afternoon.